Good evening. Today we are going to see the problems that is of gantry girder. Already I have this or we have this problem on YouTube channel, but that is from exam question paper. Now this problem is related with our term work. So now we have this problem: design a gantry girder supporting an electrically operated crane to the following data. And data is given, crane capacity is given 175 kilonewton. Span between the crane rails, actually this span we are considering as 15.4. Now why I have taken this as 15.4, that is most important. We are going to consider beam as columns. So I have this as one beam, which is first column. And I have second, we have this as another beam, which we have as second column. And now we are going to be with on this, that is gantry girder. And for that gantry girder, we have this as bracket. And on this bracket, actually, we have this gantry girder. Now we have this ISHB 300, 350, or we may require 400, and value of flange, this is generally we have 200. Now we have this as 200. Now we are using here for gantry girder, we are using ISWB again 350, 400. We have 350, 400. And for this also we have this value, that is generally we are going to consider ISW width, we are going to consider it as 200. So considering this, let us we have E from this to the center of this, that we are going to consider it as 300 millimeters. So my rail over here. Now we have beam, so this I have considered as 100 center of this. If I will plot over here, we have ISMC 250, and below this we have this beam. So ISMC 150, or we have 200. So we have this value 125, and then this 100 to 150. So 150 and then 125 we have. So 150 plus 125, this goes to 275, and we can have clearance between this column, flange, and this gantry girder. Let us we have this as 25. So likewise I have considered it as 300. So 300 from this and 300 from this, and therefore we have this span between the crane rails. This becomes, so my span of the truss, this is center to center distance, span of the truss, you have to go to span of the truss. This I have 16 meters, and then this is considered as 0.3, and this also considered as 0.3. And then this goes 0.3, 0.3, 0.6, and this becomes 15.4. So we have span between the crane rails, because rail we have at the center of this. We have center of this, we have rail. And therefore 0.3, 0.3, 0.6, and this goes to 15.4. Then weight of the crane girder 150, then 30 kilonewton weight of crab electric motor, minimum hook approach 1 meter, wheelbase 2.6 meters, span of gantry girder 4. This is my spacing of truss. Spacing of truss. And now you do not think, whatever span of truss you have, span of truss, and then whatever you have put over here and subtract from this 0.6. Remaining part we will see in the practicals. And so it goes to 15.4. If you have 14, then 14 minus 0.6, then it goes to 13.4. So likewise, you have considered this value 0.6, you subtract this value 0.6 from your span of the truss. Now we have this already we have seen. Now we have static load, that is weight of crab plus lifted load, that is 30 plus 175, 250 kilonewton at hook approach from reaction, and hook approach we have 1 meter. Then we have weight of crane girder acts as UDL, that we know already. So these values are shown over here. So we have this as 15.4. This is 1 meter, which is my hook approach. So this is 1 meter till this. And then we will find value of RA by taking moment about B0. And we will get value of RA as 205.14.4. So 15.4 minus 1, 14.4 plus 150 into from center, this will be 7.7. And divided by 15.4, we will get value of RA as 266.69 kilonewton. Then impact load for electric operated crane, we know it is 25%. So we have this value 0.25 into 266.69 comes 66.67. And we will get this value total load on two wheels 333.36 kilonewton, which is vertical load plus impact load. You can multiply this directly by 1.25 by considering 25% for impact load. And we will get from this load on each wheel, because this load will be carried by two wheels. Now already I explained this, carried by two wheels. If you will see this diagram, I will show you that is in the diagram how it will carried by two wheels. So you can see we have actually in this two wheels. One wheel we have below this and another we have below this. So two on this side and two on this side. So whatever reaction we are going to get, that reaction we have here. So carried by two wheels, and this is my wheelbase. Now this distance you can say from center of rail. So this distance we can say that we have as 15.4. So this distance, center to center distance between the rails. Now we have value that is factorial load. It comes 166.68 kilonewton, and we will make it as factorial, which becomes 250 kilonewtons. Now we will find maximum shear force. For maximum shear force, we have to keep one of the wheel load, on reaction. Wheel load on reaction. And then we will just put it on the reaction, and then we will get this value that is equal to moment. We will take about R20, and from this I will get value of R1 as 341.90 kilonewton, which becomes my maximum shear force. Now for maximum bending moment, second we have maximum bending moment. And for maximum bending moment, we have one of the wheel load and CG of wheel load. These two should be equidistant from center. So we have equidistant from center. And then you can see this. So we have this distance between these two is 2.6. This is already mentioned. So between these two, we have 1.3 meter. Now center, we have here, you can see, we have center over here, that is 2 meter. Now equidistance means this should be 0.65 and this should be 0.65. So as this again, we have 2 meter. So as this is 0.65, so automatically this becomes 1.35 meters. Similarly, we can have this distance as 1.35 meters. And then we will just take moment about R20 over here. And from this we will consider CG 500 into 1.35 minus 2.2, which is a rail plus weight, self weight of gantry girder. And from this we will get R1 173.15 kilonewton and maximum bending moment. So bending moment under wheel load. This is my maximum bending moment 231.75 kilonewton meter. And now we have to go lateral force 10% of weight of crab plus weight lifted. So that is static load. And then multiply it, and this will be carried by 4 wheels. That is 2 on left and 2 on right. And then we will find maximum bending moment. So we have 7.69, that is load carried by wheel. And when we have load carried by wheel 250, bending moment is 231.75 kilonewton meter. And therefore, for this wheel load, we will get bending moment as 7.13 kilonewton meter, that is in y-y direction. Now section modulus required, as we have this as section modulus, we are going to say we have this laterally unsupported. So we have this as laterally unsupported. Laterally unsupported. And value we are going to be with. So we have actually this, we have changes. So this value we have, that is bending moment. If we will go to this, then we have bending moment 231.75. So 231.75. And then if we will calculate this, then we have 231.75 to the power 6 into 1.4 divided by 250 divided by 1.1. It comes 1179.82. So we have this as 1179.82 into 10 raised to 3 millimeter cube. So 1179.82. And then a depth of section, we have 333.33 to 266.67, 4000 upon 12 to 4000 upon 15. And I have taken these values, 350, that is ISWB, 569 Newton per meter. And then we have, these are the properties of this section, 7250 area, TF, TW, IYY. And then I will select ISMC 250, 306 Newton per meter. And then we have these dimensions. And then from this, I will get total area of this section. That is area of channel plus area of beam. This is area of beam. This is area of channel. We have 11150. And then we have IYY total. That is 5060 into 10 raised to 4. Because now we have weaker section, that is along YY axis, not along XX axis. And therefore we have taken IYY and total area, from which I will get value of RYY, which will be my R minimum. Then classification of section, BF by 2 upon TF, 8.77 less than 9.4 plastic, and D by TW 40.9 less than 84. And therefore section becomes plastic section beta B1. Then for moment of resistance, RYY, already I mentioned it. We have this as IYY divided by total area, it comes 67.37. Now we have KL upon R, so KL 4000 upon R minimum, which we have RYY, and this comes 59.37. Then HF upon TF, D minus TF, so D we have 350 plus this 7.2, because now if you will see, we have section like this. We have this as beam, and on this beam, actually we have channel, and total depth we have 350 of beam, and this 7.2, this is TW, that is of channel, which is 7.2. So 350 plus 5.7, 7.2. So 357.2. So this is 30.33. And then we have to go to this KL upon R and HF upon TF. KL upon R, we have to take 50 and 60. And HF upon TF, we have to get 30 and 35. And from this, we will get for 30.33 value, first value 926.1. and FCRB to 659.92. And we have to find value that is for 59.37. And for 59.37, we will get value of FCRB 676.69. And then FCRB 700, 600. This is 250. And for this, we are going to get value of FBD, and that is 201.23 MPa. Now this 927, 912, these values we have taken for 50 and 60 from here. This you can see we have table 14 and we have this as table 13A. Now knowing this, we will go for YP. Now actually this is most important one, how we will find this YP. So we have this will be I section. And then we have channel above this. Now we have somewhere, we have this as YP. So YP means we have this as plastic neutral axis. Plastic neutral axis, this is axis which divides area into two parts. Divides area into two parts. Now in last problem, I have taken directly area of channel. There we have that is bending moment is very large, and if you will see your YP value, that is going to be very close to the your width of the flange of the channel, and therefore values there we will have same. But if we will go for this in the same way as bending moment is less, then you will get value of YP as negative. Now you can see we have 250 into 7.2. So we have this will be depth of channel which is 250, and 7.2 we have this, that is thickness of flange. Sorry, thickness of web, plus 2 into 14 into 1. So we have thickness of this as 14.1, and 2 we have on both sides. This is 1, this is second. YP minus 7.2. So this is YP, and we have to subtract this 7.2, means we are going to consider this area. So we have taken this area, now we have taken this second area, then 200 into 11.4. So we have this will be area of this flange of the beam, and then plus 8. Now we have this, that is thickness of web, and this distance we have to consider. So this distance will be YP minus thickness of flange. So we have thickness of flange 11.4 of beam, and minus we have this will be thickness of web of channel, and equal to this will be total area divided by 2. That will be equal area axis, and we will have this as 51.2. Now ZP we have considered. Now in this I have taken directly of this channel. Actually you can have exact, if you will to you want to go, then you can go this as 250 into 7.2 likewise, but your answer will not be changed if we will consider channel as a whole, because value you will get 51.02 and this remaining is 30, and so that moment if we will go for ZP will not be a lot change. So approximately we can consider directly that is of channel, and from this I will get value of ZP, that is equal to 1233.06 into 10 raised to 3 millimeter cube, which will gives me value of MD. Already we have seen we have FBD, that is 201.23, and this value of ZP 1233.06, and this comes 248.12, which is greater than 231.75. Now 201.23, if you will see we have this 201.23, which is FBD, and then knowing this value we can have save for this MDZ I can mention over here, and then we can have check for biaxial. So we have ZYT, and that is of top flange, because we have MDY, that is in top flange only, and therefore we are checking for top flange. So IYB of 2, because this will be half we are going to consider, we are taking top, but channel we are going to consider full, because channel we have that is to the top flange. And then this will be depth of channel. So depth of channel, because we are taking about y-axis. And from this I will get value of ZYT 357.6 into 10 raised to 3 millimeter cube. So I will get this value as MDY now, which is 81.27 kilonewton meter. And then mz upon mdz plus my upon mdy should be less than or equal to 1. So it comes 1.02, which is approximately 1. We need not require to revise this section. So my section is safe. And likewise, we have to go to the gantry girder. So we will stop here only. Remaining part we will see in the next lecture. So thank you.